Our next group of presentations will be from the Weapons and Combat Systems Division. Weapons Combat and Systems Division applies science and technology to the capability, analysis, development and operation of weapon and combat systems relevant to the ADF. Please welcome our first presenter, Alisha Coombs.
We live in an age where a vast amount of information is being produced. Every day, millions of tweets, Facebook status updates, Insta stories and more are shared, viewed and used across the world. This is unstructured information, which is text, images and audio that have no predefined data model or structure. Even though we can structure this information, can it be trusted, and is information of acceptable quality? In the near future, military platforms will be using and integrating information from multiple sources, some of which will be unstructured. This is vital to maintaining situational awareness in a joint environment. Current capabilities are unable to establish the trustworthiness and quality of incoming unstructured information. The premise behind my project is how can we use machine learning and blockchain-like technology on unstructured tactical information to incorporate structure, trust and quality within a distributed system. Information quality describes the extent to which information can improve meaning or awareness based on time, user and context factors. Information trust refers to the willingness of a user to accept information into their decision-making process. A major factor in evaluating trust is information source. Are you more likely to trust information from Wikipedia or accredited news site? Machine learning describes a set of algorithms to allow computers to autonomously improve their learning over time by feeding them new information. High Ledger is a decentralized, permission distributed ledger used for information trust, quality, and assurance between a number of known members in a network. It is a private blockchain application that extends capabilities from Bitcoin, the first blockchain. Alisha uses a consensus algorithm to verify new structured information to obtain overall trust. There's no single point of failure as each peer stores a copy of the ledger. To corrupt information, all peers need to be compromised. Alisha allows new trusted information to be reliably exchanged over an unreliable network that may include untrusted members. Transaction history cannot be altered or deleted once added to the blockchain, meaning the information source can be easily identified to establish a chain of trust. Alisha is one part of a bigger solution. Incoming unstructured information is sent to the machine learning algorithm to be processed into structured information. It is then stored in the memory and on the Alisha blockchain. Alisha is initialized with trusted known information. The trusted information is then sent to the distributed combat mission system to be utilized by end users. The information generated and processed in the future battle space will be more complex and at a higher volume. We need to be able to utilize incoming information to its fullest potential. The first step is to achieve information trust and quality. Alisha demonstrates this by creating a shared single source of truth. Without information trust and quality, information is useless. Thank you.
Thank you, Alisha. Please welcome Matthew Gerges.
Last Christmas, a UK airport was shut down for 3 days because of a single drone. Airport staff, police, and even the military didn't have any specialized equipment ready to deal with it. This incident was only one of many issues involving the malicious use of drones. Well, DST is investigating the vulnerability of drones to high-power microwave sources, which should theoretically be able to drop a drone out of the sky by interfering with its electronics. However, we first need to understand what's happening to the drone's internals while it's being interfered with. This is distinct from interfering with the drone's radio link. I've developed a pair of robots that will be used as test subjects. The leader moves in a predefined pattern, while the follower chases it using a camera, which recognizes the tags on its side. We chose to build ground rovers first, because an out-of-control aerial drone would be far more dangerous during initial testing. These two rovers are part of a larger fleet, which each have their own unique set of hardware to be tested for their specific vulnerabilities to microwaves. The rovers also live stream all their data, so we can compare it to the stored logs to recognize any memory corruption due to the interference. We had to custom build these rovers, since no on-the-market robot would be able to do everything we required of it. However, the rovers are still made from off-the-shelf components, so that if a part is damaged during testing, it can be quickly swapped out and analyzed. My focus was on the programming and electronics, which pushed me to learn a lot about data streaming and image processing. A major problem I ran into was that the flight controller didn't log data fast enough for testing. I learned how to modify and improve the flight controller's firmware, which lacked any useful documentation. So I then made tutorials on how to do it so no one else would have to struggle through the same thing. I also learned far more about the seriousness of robotic terrorism, and I believe that this project is a crucial part in combating against the malicious use of drones. And when this project succeeds, I believe that there will be one less thing to worry about. Thank you.
Thank you, Matthew. Please welcome Christopher Hobbs.
Hi there, my name is Christopher Hobbs and I'm a Master of Mechatronics student at the University of Melbourne. Today my task was to research and develop test methods for constructing high survivability avionics systems, and the effort for this was to lead to building a flight data recorder. We were building this for a flight vehicle and there was a lot of onboard experiments with it, so it was very important for this data to be recorded. It's an electromechanical system and I was focusing largely on the electrical side as well as the software. In terms of the value for DSTG, so flight data recorders already exist, so why not just get one off the shelf? The reason for this really comes from the specialised experiments that were on board. The other aspect was the testing for the flight vehicle. So it costs quite a lot and a very low frequency with which we can test. So a lot of the design work for this flight vehicle was done by simulations, and in order to verify these simulations, we wanted real data. In terms of the constraints, the number one constraint was having an acceptable data transmission rate. If this wasn't achieved, then essentially we're just putting a brick into the flight vehicle. The second constraint was the size and mass. In a flight vehicle, it just needs to be as small as possible. And the third, the surviving high vibrations and impacts, and then, of course, the price. In terms of the development status, so I've built a prototype board that can handle all these systems. It is communicating with the flight computer and developing software to interact with the other systems. In terms of the mechanical, so I'm working with my supervisor. He's a mechanical engineer. He's building the housing that it's going in. That's been manufactured and we're getting ready to perform impact tests next week. So to conclude, flight data recorders will allow for experimental data to be recorded and further our understanding and research for the experiments that are occurring on board. I brought a lot of innovation and enthusiasm to the team, so I'm up in Brisbane and I'm the only student up there, so I'm 15 years younger than I think everyone, so that's been necessary. And I've worked well with my supervisor, the mechanical engineer, to integrate this system together. Thank you.
Thank you, Chris. Please welcome Rhett Hull.
Imagine a ship in your navy deployed in the high seas. In the distance, an anti-ship missile is headed towards you. What to do? Well, you can either release a false target that says, okay, I'm a ship, you travel over there. Or you can use your other defensive missiles, which are less capable, and fire it at the superior threat and hope that one of them hits it. So instead of doing that, what we're going to do is use our missiles in an intelligent, coordinated manner in order to defeat this threat. So the first thing we need to know is, okay, where's this threat going to go? So we know that the threat is defined by some kinematic equations, and we can determine in this region on that line the threat's going to end up there at some time t. At the same time, we know one of our defenders can end up in that position too. So on the green zones, if the defenders take the right actions, they can hit the threat. But in that red zone, if the threat ever decides to go down there, no matter what the defenders do, they'll never hit it. So rather than developing a more complicated classical model, what we do is instead use reinforcement learning. So it's a bit like travelling home from work. With Google Maps, you'll use a model which will provide basically a route for you to take home, whereas experience will say, City-bound routes are usually busy, or there's usually roadworks in some area, of course, that we have to suffer through. So with reinforcement learning, we can get around this stochastic nature by teaching it by experience, basically. So what we do is we provide an action to the missile. That's a force tangent to the body axis, and that changes the direction. From that, we run it through the simulations through one time step, and then it gets a reward. How much area am I covering off of that threat? And then you get into state. So what does the new environment look like? How have things changed? And what we do is we do this millions and millions of times. So you'll end up running multiple episodes and multiple different scenarios, and you eventually develop a controller that's intelligent and can defeat any threat. So we've demonstrated this concept of reachability does work. We've tested it with a single agent, and we've also developed the high-level algorithm structure for the multi-agent. Going forward, we're going to develop an intelligent predator. So when it sees that red zone, it's going to know we're trying to look at it and take those maximal actions, but then that's going to try to avoid us and go through the red zone and escape. So like the work we do here at DST, I urge you not to do what is expedient, but to instead continue to pursue what is meaningful. Thank you.
Thank you, Rhett. Please welcome Oleksandr Pushkarov.
All right, good afternoon, everybody. So my job was in designing a small remotely piloted aircraft to perform the specific task as in the title. Ordered by the Weapons Combat System Division, it was subject to tight restrictions. Out of them were tight storage restrictions, maximum takeoff weight, flight endurance, and the capability restrictions. So it had to have semi-autonomous mode capability and be easily repairable in the field after a crash landing. Various design decisions were made, and we decided to use a quadcopter configuration due to its mechanical simplicity, ease of control, and a potential for safe landing with one motor seizure. We decided to use off-the-shelf electronics. However, the frame should be 3D printed for rapid reprototyping in-house. To fit the storage dimensions, it was decided that the arms should be foldable. The problem was subdivided into two subsections. One was solving the electronics integration. That was the job of MK1. The work was started on the 5th of March and culminated in a successful flight test on 30th of July, indicating that all the electrical and electronic compatibility problems were ironed out and the systems worked as intended. After a successful flight test, we moved on to MK2. After several iterations, the final model for a foldable drone looked as follows. Work began on the 6th of August and culminated in a successful flight test on the 21st of September, which indicated that all the outcomes were achieved. The frame itself was 3D printed from polycarbonate, lightweight but durable material. It was foldable and modular construction. The arms were made as a plug-and-play system. It has semi-autonomous flight mode capability through Mission Planner on the Quadcopter software. So it fitted all the requirements that the Weapons Combat System Division made. Out of lesson learned and in this project, there are several, but you could summarize them in engineering perspective when you get a complex problem, subdivided into several sub-problems, and each solution put it back to get the final solution out of it. From the management side of things, it's impossible to know everything. So at the onset of the project, it's important to define the SMEs for various subjects, various areas, and continuously liaise with them for the successful outcome of the project. Future work is to determine the flight algorithm to recover from a mid-flight collision, which would result in a rotor loss and a safe landing. Thank you.
Thank you, Oleksandr. Please welcome Lindsey Paul.
Hi, I'm Lindsey and I worked on SPAD technologies. So what is a SPAD? A SPAD stands for Single Photon Avalanche Diode, which is it's just a diode that can detect individual photons. So say we've got some object that we want to be able to detect. We use an illuminator, such as a laser, to send out photons, which will then hit the object, and some of those will reflect back and hit the SPAD, which will detect that the photon has hit it. So just like the chips in your camera, just like the pixels in your camera, we can combine a bunch of these SPADs together to form an array, which will take an image of the object that we're after. So this allows for two modes. The first one is just counting the number of photons that hit it, which gives an intensity image, which is just like black and white on your camera. But the main advantage is that we can image in 3D. So this is done because we know how fast photons travel. So we can time how long it takes from when the photon leaves the laser to when it hits the object and then it returns. So with that distance estimate, we can actually map in 3D the object in question. So this is a live version of it done at DST in a dark tunnel. So you can see it works quite accurately in terms of depth measurements. But why is it done in a dark tunnel? So the SPAD can't differentiate between a photon that's from the laser itself and one that's just in the environment, such as sunlight reflecting off water, for instance. So part of my project was doing a review of classical image processing methods to actually detect the object, which you can see down here. It's almost impossible to see it before that image processing has been done. So that's the finished product there. So how do you reduce the amount of noise? So currently a 256 by 256 resolution SPAD's in the works at DST. When that's finished, it'll be the first in the world of that type. So this, improving the resolution, reduces the effect of noise on the image that's found and actually improves shape information, which is important for classification of what the object actually is. So my main contribution with that was writing the FPGA code. So an FPGA is the board that interfaces between the computer and the hardware itself. So I was actually writing FPGA code to control the electronics. So there's an individual circuit behind each SPAD that needs to be controlled. So it's getting controlling that, getting the image, and then porting it back to the computer. And if anyone's worked with SPAD, they'll know why that's quite a complex task, especially for someone who's never done it before. So that was my contribution there. And also attaching all the equipment onto the drone itself. So in the future, the hope is to use these SPAD images to feed into a neuromorphic algorithm, so it's just machine learning, to actually automatically classify what the object that we're seeing is. So that's excellent. Thanks.
Thank you, Lindsey. Please welcome Luke Smith.
Autonomy is the future. We want machines to handle difficult and mundane tasks so that we can focus on new and unique problems. We want machines to interpret vague instructions, such as deliver this package to this location or locate these hostages. But what we don't want is for changes in the environment, such as lighting or movement, to prevent the machines from completing their tasks. To achieve both these requirements, a fuzzy logic controller is a good choice because fuzzy logic allows machines to handle with partial truths. Consider the rules for speed control. If obstacle is close, then slow down, and if obstacle is far, then proceed. We can define two membership curves, which we use to determine how much a given distance belongs to each of these categories, close and far. For example, an obstacle at this distance is closer than it is far, and so we slow down. But an obstacle at this distance, it belongs more to the far category than it does to the close category, and so we proceed. Ultimately, it is the shape of these membership curves which allow fuzzy controllers to handle virtually any scenario thrown at them and deal with noise. Now in our case, we use a global optimizer to automatically tune these parameters for us to control a drone to navigate an obstacle course to a target. The drone scans its environment and locates the target relative to itself and feeds these as inputs into the controller to tell the drone in which direction to move. Now, initially, our controller was random and unpredictable. But using the global optimizer and a long time of iterating through it, we created controller behavior more like this, which still isn't optimum but is much better. Now, optimum, the definition for that is determined by a fitness function, which we define, and choosing this fitness function is perhaps the most important part of the process since it defines success and failure. Now, provided that our initial guess of parameters is good enough and our global optimizer meta parameters are well selected, the optimum solution should eventually be found. Now, the next step of this task is to coordinate multiple drones to arrive at their targets simultaneously, the potentials of which have been described in various pieces of fiction, including the movie Big Hero 6, to great effect. And I believe that with a small amount of internal restructuring, this complex task could automatically be solved with a very small amount of internal effort. And in the end, that is what autonomy is all about. Thank you for listening.
Thank you, Luke. Please welcome Vidar Son.
Good afternoon. My name is Vidar, and I was an IEP student at DST Edinburgh. My work was on counter IED, and my project was to develop an autonomous target detection system to detect buried IEDs. My project utilized GPR to image the subsurface of the ground, and machine learning to determine if these images contained a target or not. So firstly, what is GPR? GPR stands for ground penetrating radar. GPR works by emitting electromagnetic pulses into the ground. These pulses are then reflected back to the sensors by the materials in the ground. As the materials have different dielectric properties, they reflect these pulses back at different intensities. And by measuring these intensities, we can produce a GPR image. So this is an example of an image produced using GPR. Each vertical column of pixels corresponds to a single GPR scan, and we produce the full image by collating all of these GPR scans. So now that we have these GPR images, we can try and automatically find where if it has a target or not within it. There are a few challenges with this. Due to the nature of IEDs being improvised, we have no clear target profile to go with. There is also another challenge with the GPR images themselves, as they are full of noise. And it's often hard to differentiate between valid targets and background clutter. So taking these into consideration, we decided to use machine learning to develop a classification model. So the way the classification model works is it utilizes a training dataset to, first it utilizes a training dataset and we label these images as either target or non-target. These images are then broken down into a set of features, and these features are then used to train the classifier to determine what features are prevalent in targets and which features are prevalent in non-target images. So after training the classification model, we can then use it to predict new images, if it is a target or non-target, based on the features prevalent in this image. So after training the classifier, we applied it to some test lanes. And the result of this was that we were able to detect the majority of targets. We have low false alarm rate, and the project is going to continue as we hope to develop it into a more complete system. Thank you for listening.
Thank you, Vidar. Please welcome Nicholas Steele.
So at some point, I'm sure we've all experienced network connectivity issues and the frustration that comes with waiting for a new piece of information. We take this same example and put it into a tactical environment, we can imagine its life-threatening implications. So tactical networks present one of the most challenging environments for military communications. This is due to the diversity of platforms used and complicated communication paths. Our goal is to experiment with scalable, dynamic, and affordable approaches capable of delivering trusted, timely and relevant information. I've researched the feasibility of 2 prototype software solutions. The first is designed to automatically organise newly generated data at the edge of the network. We can program what new data we allow into the system using a minimum content difference threshold, meaning that only new and worthwhile information is considered. The data that is allowed into the network is associated with a calculated value metric. The value metric is used to rank information based on importance. It considers that different information may be of different value to different end users based on their mission objectives or role within the system. This mitigates some requirements for cloud processing, which can be resource heavy and expensive. The second solution is installed on each node and is designed to increase information availability within peer-to-peer networks, working in conjunction with the first solution, but responsible for distributing the information to end users. This is achieved through a publish-subscribe-driven architecture, observing network conditions and strategically replicating metadata to subscribe nodes during opportunistic timeframes. This research has enabled me to find direct areas of compatibility with a DST-developed framework called RISE. RISE has been developed to experiment with adaptive information techniques. It has been used in a tactical-like environment with Surf Lifesaving South Australia, in which Surf Lifesavers were tasked to respond to numerous emergencies using the framework's functionality. In going forward with RISE, it is possible to implement the key features of my research. For example, configuring selected nodes to have greater network priority, collecting and sieving only important information generated from sensors, or only updating the GPS positioning of Surf Lifesaving assets if a threshold of geographical displacement is met. This threshold value can also self-configure based on what is possible with current networking conditions. It is also possible to predict what nodes will likely use a certain piece of information in the future and prepare it for immediate use upon an end user's request, all factors contributing to tactical network optimization. So consider that it is possible for governments to purchase highly technical equipment, but by optimising processes such as replacing network-intensive tasks with strategic software filtering and dissemination, we're able to recognise areas that can establish a tactical edge. Thank you.
Thank you, Nick. Please welcome Jack Taylor.
Hello everyone, I'm Jack Taylor. The military operates with uncertainty. Imagine going through this mess, clearing it out room to room. Every footstep's going to be a risk. There are probably IEDs and you could get ambushed from all sides. This is a critical question faced by the ADF. How do we provide our personnel operating in such environments with a decisive advantage? What if we didn't have to risk them at all? One answer is drones like these, and lots of them. We can send in large swarms of low-cost micro-aerial vehicles to map the area, identify targets, and even engage threats. Large numbers of these vehicles are far more effectively able to cover the urban battlefield than a small number of well-equipped, highly expensive drones could possibly hope to. My task at DST was to develop the high-level flocking framework to generate the swarming behaviour. Initially, I was given a simple 2D Python simulation, in which a number of drones simply moved towards a target, ignoring one another. As my role was to implement intelligent flocking, I coded for 3 behaviours: grouping, separation, and velocity alignment. Essentially, these bring the drones together, maintain spacing within the swarm, and match velocities to the target. In such swarming algorithms, complex behaviour emerges from access to local rather than global information. Therefore, I created a line-of-sight function to model the drone's communication systems, where we applied the constraint that only drones within line of sight can communicate. This diagram here shows the perspective of Drone 1. Drone 1 has line of sight to Drone 2 and Drone 3. Therefore, they are part of the local net. Accordingly, the flocking algorithm commands Drone 1 to separate from Drone 2, as it is within the separation radius, while moving to group with Drone 3. Concurrently, Drone 1 matches velocity with Drone 2 while maintaining a bearing to the target. Again, Drone 4 is not part of the local net, as it is not within line of sight. This functionality is operational, and it has been tested in a range of environments, an example of which you can see here. This is an overhead view of approximately 30 units moving through an urban environment. For this, I did create basic obstacle avoidance. However, smart or intelligent avoidance is being completed in a parallel project therefore flocking was my priority. I also implemented data logging to analyse the situation after the fact and to open up avenues for machine learning. Moving forward, I'll continue this for my engineering honours project. The focus of this will be creating new behaviours such as swarm splitting and dynamic target reassignment. All of this is to be autonomously learned by the swarm. So I will create a virtual robot gym to teach these drones to teach themselves. The overall objective is the control of large swarms in three-dimensional battle space, and this work supports DST's trusted autonomous systems research. Thanks for listening.
Thank you, Jack. Can I please have the Weapons and Combat Systems Division presenters on stage? Does anyone have any questions?
Lindsey, I was just wondering, what was the algorithm you used for the resolution increase? Or
Sorry. The resolution increase. So the image processing was just done at that resolution. But the resolution increase is by physically manufacturing with, instead of 32 by 32 there, it's going to have 256 by 256, so it's actually manufacturing a new board.
was that through some interpolation or something?
No, it's you have more pixels in it. It's like a higher resolution camera.
Oh, okay, sorry.
No super resolution.
Okay. Yep. Thank you.
Any more questions? The back?
Yes, I had a question for Jack. With your flocking algorithm, I was wondering, did you take any inspiration from natural examples of flocking?
Yeah, there has been a number of papers looking at this. The natural inspiration we took was mainly from the flocking of birds or the schooling of fish and the sub-behaviours that make up the actual swarming behaviour itself. So, yeah, we did.
I have a question for Vidar. So you mentioned training your machine learning technique, and there were potential issues in terms of the data you used in there. Was it better to have higher quality images or lower quality images in terms of target detection through your training data?
High quality images were very important, so I had to manually curate all of the images used for the training.
I just had a quick question for Ashley on how are you determining what a trusted source is, and what are you doing with the untrusted source data?
So we're using this machine learning turns unstructured information to structured information. So that's more in the information quality. And then the blockchain technology uses the consensus algorithm to verify the information to increase the trust. And also because all the transactions are stored on the blockchain, you can determine the information source. So there's multiple factors for information trust, like the correctness, the timeliness of the information, the accuracy, and we're the blockchain is using to facilitate storing information and then being able to determine if you can trust it.
In the storing of the information, are you associating a certainty with the data based on the different sources that are coming in, or?
That's one of the future projects that we want to work towards. I was only in my short 4 weeks working on the blockchain able to set the system up and work on making multiple peers and multiple organisations to communicate with each other. But that's definitely in future plans.
Thanks.
Thank you.
And there was one question here.
Yeah, sure. My question was also for you. It's Ashley, was it?
It's Alisha. Sorry.
Okay. I think it was sort of partly covered, but was the blockchain you mentioned one you would was it one that's newly being developed, or was it a DST developed blockchain, or was it?
It's actually open source software. So I adapted the Hyperledger Fabric software that's online, and then I changed the code to make it into a tactical environment. But yeah, it's all open source software that you can download and play with yourself.
Hi, Alisha. This question's for you as well. Did you give any thought to the impact of having an immutable ledger of information of defence communications?
The blockchain also has crypto. It's all encrypted, all information, so only the nodes have access to it. So where it's being transferred between the different nodes, and as it's stored on the blockchain, it's only stored as a hash code, so you can't just leak into the system and get the information. And because I made a permissioned blockchain, you have to have access and be allowed into the network first, because like Bitcoin is a public one, so anyone can have access as long as they have the computing power. But by making it private, it's applicable for a tactical environment.
Okay, thanks.
Thanks.
Thank you to all the Weapons and Combat Systems Division presenters this afternoon.
Okay, that brings us to the end of our student presentations today. Can we just get one more round of applause for all of the students who did present?